So section 9.1 actually picks up wherever geometry left off. So for those of you who don't remember, geometry probably left off right before quarantine with you needing to, I don't know how far you got, but you probably had to start learning some SOHCAHTOA on your own. The fact that we shut down when we did, you had probably seen some SOHCAHTOA and then had to apply those SOHCAHTOA things on your own. So this is all section 9.1, and 9.1 is all about right triangle trig. We are going to add a few things to what you didn't do last year. So last year, you focused on understanding SOHCA and TOA, right? You heard a huge story about SOHCAHTOA, and then hopefully it made you remember the name SOHCAHTOA because that's kind of the reason it exists. But the name SOHCAHTOA exists as, I don't remember what this thing is called, maybe like a mnemonic device or whatever.
Yeah.
So this thing is existing so that you know what goes with what, right? S stands for sine. Now, I'm always, as well as your book, going to use this symbol, and this symbol is theta. Okay? So that symbol is called theta. It literally means the same thing that X does. Okay? Theta is a variable. It's a Greek letter, but the Greek letter is just an unknown. It's just a variable. It's the same as using Y or X or Q or R or T or whatever. It's just a variable. Okay? So sine of theta was equal to the opposite over the hypotenuse. And that's where all of those letters came into play from so. S stands for sine, O stands for opposite, H stands for hypotenuse. Now, as we continue on, we could do cosine of theta. That's equal to the adjacent over the hypotenuse. And then the tangent of theta is equal to the opposite over the adjacent. Now, that's all well and good, except for the fact that I don't remember which one the opposite is. I don't remember which one the adjacent is, and I don't remember which one the hypotenuse is. If you don't know those, it's going to make this impossible for you to do right triangle trig, right? So first off, understand or remember that this only exists with right triangles. This does not exist with anything but a right triangle. I will never ever use the right angle. Okay? So when I'm using SOHCA and TOA, I am never ever going to use the right triangle. I'm always going to use one of the other two angles. Okay? Doesn't matter which angle you pick, but whichever angle you pick as your reference angle is going to change which side is the opposite. It's going to change which side is the adjacent. It's never ever going to change the hypotenuse though. No matter what, I haven't put an angle down here yet. This is always going to be the hypotenuse. Okay? So no matter what, the angle across from the right angle is always the hypotenuse. The one that's slanted, the one that's the longest is always the hypotenuse. Okay? Now, it doesn't matter which angle you pick, but let's say I chose this one to be angle theta. That tells me where my opposite is going to be, and it tells me where my adjacent is going to be. Opposite is always the one that is across from the angle. Oops. Opposite is always the one that's across from the angle. And adjacent is always the one that is touching the angle. See how this side is touching that angle? That's the adjacent. Now, just so you know, and just so that you can kind of use this in the future, let's say we have the exact same right triangle, but we use the other angle this time. That just changes where the opposite and the adjacent are. So this one is going to be the new opposite. This is going to be the adjacent. This is going to be the hypotenuse. Okay? So that's what you learned in a nutshell in geometry. You had the ability to set up the equation. You had the ability to solve the equation. This is usually used when you're trying to find sides of an angle, or sides of a triangle. We also have the ability to find the angles of a triangle using the inverse sine, inverse cosine, inverse tan. Okay, so those are things that we have used and can use in order to help us solve things. We're going to take it one little step further. Okay, there are three other trig functions that people don't really hear about until they get into either upper level algebra 2 or calculus. And those other 6 trig functions are secant, cosecant. Actually, let me write it this way. So there are other trig functions that we can also use. Now, in all honesty, there really isn't that much you can do with these right now, other than make the questions more challenging. Okay, that's really the only reason that these exist for us, at least right this second. okay? So when we're dealing with these, I want you to understand that a lot of people try to relate, they try to relate secant and sine, they try to relate cosecant and cosine, they try to relate cotangent and tangent together. And you have kind of the right idea, but it's kind of tricky to remember which one goes with which. So this is something we have to pay attention to. First off, abbreviations of these. Cosecant is abbreviated CSC of theta. Secant is abbreviated SEC of theta. And cotangent is abbreviated COT of theta. Okay. Now the relationship that they have is cosecant is equal to 1 over sine theta. Secant is equal to 1 over cosine of theta. And cotangent is equal to 1 over tangent of theta. Okay. So we're going to rewrite all of those so that you can see all 6 of them in the same line. But this is just a brand new addition. And I'm telling you right now, if you know how to deal with sine, cosine, and tangent, then you absolutely know how to deal with cosecant, secant, and cotangent. Okay, it may not seem like you do at this moment because it's brand new, but I'm telling you right now, if you feel comfortable with SOHCAHTOA and TOA, then you feel comfortable with these because it's a very simple thing. Okay, so we start out, sine of theta, we said was equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And tangent of theta is equal to opposite over adjacent. Now we had said that cosecant was equal to 1 over sine. The way that you can think about this is basically just the reciprocal. Cosecant of theta is equal to the reciprocal of this. So it's going to be h over o. Cosine goes with secant. Secant of theta is equal to h over a, and cotangent of theta is going to be equal to a over o. Okay. So realistically, like I said earlier, if you can come up with a relationship between sine, cosine, and tangent, then you can very easily come up with a relationship for cosecant, secant, and cotangent. Okay. So let's start out with a relatively easy thing, because what I'm going to do is I'm basically just going to give you something that says evaluate all 6 trig functions or find all 6 trig functions of something. Okay. So is everybody good here? Everybody got this? You're fine. As long as you know the relationship between sine, cosine, and tangent, opposite, hypotenuse, and adjacent, and you remember that sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent. As long as you remember those, then you should be able to create all of these relationships. Now, the easiest way that I think about it is, so if you remember, this stands for cosecant. If you look at this, every one of them, everything in this line has one with a co in it and one without a co in it. So sine doesn't have the letter CO in it, but cosecant does have the letter CO in it. Cosine has CO in it, secant does not have CO in it. Tangent has no CO, and cotangent does have a CO. So that's the way that I always relate it to myself, because I know sine, cosine, and tangent already. But if I'm thinking about this, tangent and cotangent, that should be easy. You know, those go together. With cosine, I just pair it with the one that doesn't have the co. And for sine, I pair it with the one that does have a co. So this one does not have a co, this one does, this one does, this one doesn't, this one doesn't, this one does. So that's the way that I've always remembered it, and it's made the most sense to me. If you have a different way of remembering it, that's fine. But it's just something that should hopefully help. Okay, so your directions on this are to find all 6 trig functions for okay, so I'm going to give you a second to try this on your own. Okay, you should be able to find what sine of theta equals. You should be able to find, actually, I couldn't give theta yet. So you should be able to find what sine of theta equals. You should be able to find what cosine of theta equals and tangent of theta. And then you just have to go through and find the reciprocals of these. So I'm going to give you a second to try it out. All right, so if we're finding all 6 trig functions, the very first thing you should do is write down all 6 of the trig functions. So that way, when you figure out what it is, you can just plug it right into this box. So sine, cosine, tangent, and then cosecant, secant, and cotangent. Now, if I were you, what I would focus on in this lesson would be the relationship between sine and cosecant, cosine and secant, and tangent and cotangent. I would try to get those figured out because all you have to do is figure out what sine, cosine, and tangent are and then flip them and you're done. As long as you have the relationships described correctly. If you don't have the relationships described correctly, it's going to get kind of challenging for you. Okay. So what I would do is I would say, okay, if this is my angle, I know that this is my opposite side. I know that this is my adjacent side, and I know that this is my hypotenuse. I need to find the hypotenuse. How do you find the hypotenuse? Using the Pythagorean theorem, right? So we could do it a couple different ways, but I want to use the Pythagorean theorem because that's the easiest. So I've got 5 squared plus 12 squared. What's it equal? It's 13. So most of the time, these are going to work out pretty nicely to give you a Pythagorean triple, but sometimes they don't. So just got to keep that in mind. Where most of the time they should be nice, easy Pythagorean triples, but sometimes they're not good. All right. So sine is equal to opposite over hypotenuse. So opposite over hypotenuse is 5 over 13. Cosine is opposite or adjacent over hypotenuse. So it's going to be 12 over 13. And tangent of theta is going to be opposite over adjacent, which is going to end up being 5 over 12. Now, this is why it's really important for you to understand sine, cosine, and tangent, because all you have to do for the next 3, should be 3 free giveaway points, is flip it. So this should turn into 13 over 5. This should be 13 over 12. And this one should be 12 over 5. Right? Now, one thing to kind of think about here is every single one of these values should give you the exact same angle. Okay? Every single one of these values should give you the exact same angle. All of these are equal. All of these ratios are equal to each other, which means that every single thing that you plug into your calculator should spit out what the actual angle is. I don't know if the angle is off the top of my head, but they all should work. Okay? Any questions on this or issues on this? Okay, yeah. But,
why for the other 3? Why they exist?
as of right now, there isn't a huge reason for them.
Oh.
Once you get into calc, and maybe this year, we'll see. There's a lot of like trig simplification that happens. And sometimes it makes more sense to deal with cosecant, secant, and cotangent than it does to deal in the other ones. Sometimes it does. Most of the time, it doesn't make sense to deal with anything other than sine, cosine, or tangent. So as of right now, it's going to seem like this is 100% useless. If you end up taking calc or end up going a little bit further in algebra 2, it's going to make sense as to why we use it.
Okay.
But as of right now, there really isn't a reason other than just knowing. Okay. So here's kind of a trickier way of asking you the same kind of question. But it says something like in a right triangle, I spelled the word in wrong. In a right triangle, sine of theta equals 4 over 7. And then it would say something like find the other 5 functions. So here, what I would do first, and this is exactly like an SAT style question. This is exactly the same way the SAT style questions start, where they give you something and then it looks like they don't give you anything else. Start by drawing a picture and defining what sine of theta equals 4 over 7 looks like. The other thing that's tricky about this is you have to keep your answers exact. So you know I said on the last example, a lot of the time you're going to have Pythagorean triples. This is not a Pythagorean triple. Okay. So when you find your third side, keep it exact. Keep a square root in your answer because it needs to be there. Okay. So again, I'm going to give you some time to work on this. Make sure you understand how it works. All right, so it starts out, we have to come up with a triangle first. So the first thing you should do is draw your triangle. So we have a right triangle And it's very important that, that you create your relationship correctly. I don't care which angle you choose, but your relationship has to be correct, because if your relationship is not correct, it's going to throw off all other 5 of them, and that's going to suck. Because if all other 5 get thrown off, that means everything's going to be wrong. So it doesn't matter if you choose the top angle to be your angle or if you choose the bottom angle to be your angle. I always choose the bottom one just because that's what I always do. But you choose what makes sense to you. Okay. So this angle right here, that means that this is my opposite and this is my hypotenuse. So if I have sine of 4/7, that means that that one angle is my opposite, other angle is my hypotenuse. So now if I'm wanting to find this side right here, I'm going to do the Pythagorean theorem. So it's going to be 4 squared plus x squared equals 7 squared. So that's going to be 16 plus x squared equals 49. We're going to subtract 16 from both sides. So I'm going to get x squared equals 33. And then square root. So now I'm left with x equals the square root of 33. This is where these things get kind of nasty because they have a radical in them. And you have to leave the radical in there because with these functions, you have to be exact. The directions for most of these are going to tell you to be exact. Okay. So x equals the square root of 33, which that gives me my third side. Once I have the third side, this should be a very, very simple process because it's the same every single time. So even if I have the sine value given to me, I like to write it again just to make sure that I've written everything the same way every time to be consistent. And then it just turns into look at the picture and write down what's supposed to go where. So sine theta is going to be 4/7 that was given to me. Cosine of theta is going to be the square root of 33/7. And then tangent of theta is going to be 4 over the square root of 33. Now here's a little bit of a tricky part. Okay. Here's a little bit of a tricky part. And I'm going to go through and rewrite all of the other ones first. But you're not allowed to have radicals in the denominator. Right? That was never something that we were allowed to have. We're never allowed to have radicals in the denominator. Since we're not allowed to have those, we need to get rid of them. Okay. So I'm going to get everything written down first, and then I'm going to go through the process of getting rid of the radicals in the denominator. So you can see that there are 2 here that are going to end up being an issue. That one is an issue, and that was an issue, but they're both handled the same way. So they're both handled the same way. The way that you get rid of them is you multiply by the bottom, whatever the radical is. So this one, if it's 4 over the square root of 33, we multiply by the square root of 33 over the square root of 33. Then you multiply through and you end up with the 4 times the square root of 33 over this times this just gives you 33. So that is the answer that Big Ideas is going to expect from you. Okay. So that's the one that they're going to expect. They have to do the same exact thing with 7 over the square root of 33. So 7 over the square root of 33, we multiply by the conjugate. So we end up with 7 times the square root of 33 over 33. So they have to be rewritten without any sort of radicals in the denominator. Okay. Does anyone have any other questions or issues or anything when it comes to the 5 trig functions, 6 trig functions? I think it's pretty straightforward, honestly. At least I'm hoping so. Pretty straightforward lesson for us to kind of jump back into. The last thing I want to do is I just want to go through solving a triangle so that you can see it. So that way you know for sure. So that way you know for sure how to use the trig functions that we learned in geometry. So let's go through an example that looks like this, where we have a triangle. And we want to solve the entire triangle. So this is asking us to solve triangle ABC. It's giving us that this one is 32. And this one is 10. Okay. So we're trying to solve an entire triangle only knowing 2 pieces of information. We know one angle and we know one side. Now, once you know some other things, you can start to kind of piece together and move a little bit quicker. But with this, it becomes a little bit challenging because I only know a couple pieces of information. one thing should be pretty easy to find, and that should always be the other angle. If you're given one angle, the other one should be pretty easy to find. What do I have to do to find that angle right there? Subtract the other one from 180, right? 180 minus 90 minus 32 gives me 58. So there's 58 degrees for that angle right there. Right? Now the other two sides, that becomes a little bit more of a challenge. So if I'm looking for the other two sides, I have to take this angle right here and use one of these two sides to figure out the other one. So I know that I have the adjacent, like this is the adjacent side. And let's say that I want to find the hypotenuse. You can do this to find the opposite as well. It's not going to change anything at all. But let's say I want to find the hypotenuse first. I'm going to start this out by saying the cosine of 32 is equal to the adjacent, which is 10, over the x value, or over the hypotenuse, which is our x value. Right? Now, the way that I've always liked to do this is I've always liked to cross multiply. So this is saying the same thing as 1. So that is saying 10 times 1 is 10 equals x times the cosine of 32. Big tip here to make sure that you're doing, make sure that you have your calculator in degrees here. Okay, so hit the mode button on your calculator, and then when it starts blinking, it says like radians or degrees. So on your calculator, it should have a spot where you say mode, and then it should say radian or degree. Make sure your calculator is in degree mode here because it's not going to give you the right answer if it's in radian, right? If you're thinking in degrees, your calculator needs to be thinking in degrees. So now I would end up just in order to solve for x, I would divide by cosine of 32. So my answer is going to end up being 10 over the cosine of 32. 10 divided by the cosine of 32 is 11.8, which should hopefully make sense if I think about it. 11.8 is longer than this side, so that's good. Now, what way should I find the last side? I could use the Pythagorean theorem. You could do Pythagorean theorem if you wanted to. You don't have to if you don't want to. But I use the Pythagorean theorem whenever possible because it's the easiest for me. So this is going to be 10 squared plus, we'll call this x right here. So x squared equals 11.8 squared. This is going to be the same thing as 11.8 squared minus 10 squared. Square root that. I'm getting 6 point about 3. Okay, and now I solved the triangle. I found every side length and I found every end. Yeah.
So, do you have like a decent margin of error for this? Because
I
feel like
usually
there's
just round it to the nearest 10.
yeah,
Yeah.
I feel like there's a lot of, I don't know, like every time I do Pythagorean, it's gonna be different than the exact answer.
It should be pretty close. I mean, like if you had an answer of like 6.15, that's probably a rounding error. If you had an answer of like 8, that's wrong. You know what I mean? So as long as it's relatively close, because even if you take the cosine of 32, which I usually use to 4 decimal places, even if you only do that to like 2 or 3, it's probably still only going to knock your answer by like a couple tenths. So it shouldn't be that much. Yes. 10 times sine of 32. You'd have to use tangent. So opposite, and if you're using the opposite, so like where x is right now, that's what you're talking about. Yeah, you have to use tangent, but you could still do that. So you would start out, you would say the tangent of 32 is going to be equal to x over 10. So it ended up being x equals 10 times the tangent of 32. But yes, you could do that too. Yep. Any other questions you guys have? All right. So you guys will have a big ideas assignment. I'm releasing it to you in just a second.